Hello folks, this video is not really from one particular section in your textbook. It takes a couple of different ideas that are spread throughout all of the conic sections, but I'm teaching them to you now all at once rather than kind of as we went throughout learning the conics. So the first topic we're going to talk about is something called eccentricity. And so here's the deal. Any conic section that we've dealt with. So think circle, ellipse, hyperbola, parabola. Any conic section can be defined as the locus of points, and that just means a collection of points, a locus of points whose distance to a point, which is called the focus, and a line, which we call the directrix, are in a constant ratio called the eccentricity. Eccentricity, we're going to denote with a lowercase e, is defined as C over A. So this is a big takeaway. This is something that I would put on my note card. E is equal to C over A. So E is right along in there with just like all of the other qualities of an ellipse or parabola or hyperbola. It's another part used to describe one of its features, just like the location of the focus, just like the location of the directrix, just like the location of the vertices, how far it is stretched, the values of A and B, and that's it. And so it's found by taking the ratio of C to A. Now, we probably know what A is without much thought because we recognize A from the equations, but C, it may have been a little while since you've done a question on an ellipse or hyperbola, so I want to recap really quickly. For an ellipse, our equation is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. And of course, we know also that our x minus h and our y minus k could switch spots. But the key for an ellipse is A is always bigger than B. So we also defined when it had to deal with the location of the focus that when you try to find the location of the focus, you had to solve for C. And C squared for an ellipse is defined as A squared minus B squared. And we subtract in that order since we know that A is bigger than B. Okay, we also know that for a hyperbola, its equation is x minus h squared over a squared minus y minus k squared over b squared is equal to 1. And A is not necessarily bigger than B. X does not always have to come first. The main thing though is that at least just one of them is negative. And then when we found its focus, we had the relationship between A, B, and C as C squared was equal to A squared plus B squared. So we used these features to find the foci of these conic sections to be able to graph them. We're going to use the same equations for A, B, and C in order to find the eccentricity of a conic section. So let me show you a picture. You don't need to draw this. This is more so for you to kind of understand what the heck we're talking about here. Eccentricity can be thought of as how much a conic section deviates from a circle. Okay, that's kind of how you can think about eccentricity. And I say that because the eccentricity of a circle is 0. So in a circle, the eccentricity is equal to 0. Okay, and you can see in this example here, the red circle, where it says E is equal to 0. From that, we have an ellipse, which is the yellow shape, and its eccentricity is between 0 and 1. So let me do this. Its eccentricity is between 0 and 1. So again, C to A. So it's going to be that ratio of the distance from F to M as M is to M prime, that point on the directrix line. And that one, it says, has an eccentricity of about 1/2, which is about right, because if you look at the distance from F to M and say, okay, that's 1, even though we don't know what that length is, it almost looks like M to M prime is double that. So that would be an eccentricity of 1 to 2, or 1/2. A parabola is literally defined having the same distance from the focus to the directrix, which is why it's always going to be in constant ratio. So its eccentricity is equal to 1. Any distance from the point on that focus to the parabola will always be the exact same as the distance from that point to the directrix line. And then a hyperbola just has an eccentricity that's greater than 1. Greater than 1. And of course it could go all the way up to infinity. So the directrix line itself would have an eccentricity of infinity. So you don't need to sketch this picture. I would write these qualities over here. But that's just for you to kind of have an understanding of what kind of property eccentricity is. Now, obviously, a circle's eccentricity is always 0. A parabola's eccentricity is always equal to 1. So we're really just going to explore the eccentricity of an ellipse and of a hyperbola. So I've got 3 examples for you. Okay, I'll say write the equation of an ellipse, and you can shorthand these directions as always. Given its focus is at, I'm going to have to use my pen because I don't have this key. Given the focus is at plus or minus the square root of 5, comma 0, oh goodness. Okay, plus or minus square root of 5, comma 0. And that the eccentricity is equal to the square root of 5 over 3. So write the equation of an ellipse given this focus and this eccentricity. Well, for the sake of not having to write our equation all over again, our equation for an ellipse is going to be this here, right? X minus h squared over a squared plus y minus k squared over b squared is equal to 1. So I need 4 things. I need h, k, a, and b. Well, the only thing I have is my focus, and I have E. So I need to use this information in order to solve for A, B, H, and K. So the thing that I would remember is that the focus of an ellipse, and I say remember, again, you can make this on your note card, so just somewhere in your chart. The focus of an ellipse is given by H plus or minus C, comma K. So if the focus is plus or minus 5, comma 0, and I align that up here, or sorry, plus or minus square root of 5, comma 0, then that's telling us that this implies that H and K, that are center point, H must be 0 and K is also 0. So there's H and K. And then it's also telling us that C is the square root of 5. Like C for the variable, not the center point. Maybe I should have left this not as confusing. Okay, so this is the center point, H and K. C, as again, the part of our ratio, is the square root of 5. So always start with the focus, because sometimes, and you'll see here in the other examples, eccentricity is reduced. So even though eccentricity, as we defined earlier, is given by C over A, sometimes it's the reduced version of whatever C over A is. Now, since we know that eccentricity is the square root of 5 over 3, and we've already double checked that C is the square root of 5, then that implies that A must equal 3. Okay, so I have my center, I have H and K. I have A. The only other thing that I need is B. Well, again, if you remember our relationship between A, B, and C for an ellipse, that C squared is equal to A squared minus B squared. Then we can substitute in our values for A and C. We knew C over here. And then solve for B. So C squared, that'll be the square root of 5 squared equals A squared will be 3 squared minus B squared. The square root of 5 squared is just 5 equals 9 minus B squared. And then you can subtract 9 from both sides, or I actually would probably move B squared to the other side so that it's positive over here, and then subtract 5 from the right side and get 4. So if B squared is equal to 4, that implies that B is plus or minus 2. So when I substitute these values into my equation for an ellipse, x minus h squared, so it'll be x minus 0 squared over a squared, a is 3 squared, plus y minus k is also 0 squared over b squared. Now b was plus or minus 2, so the thing is, when you square a number, whether or not it's positive or negative, it's always going to end up squared, so you really don't even have to write the plus or minus. And then when I reduce this, I end up simplifying it to x squared over 9 plus y squared over 4 is equal to 1. So that's the equation of ellipse that has the eccentricity of the square root of 5 over 3. So that's an example of doing it for an ellipse. The next two examples are going to come from talking about the eccentricity of a hyperbola. All right, so example number 2. I want you to write the equation of a hyperbola. Write the equation of a hyperbola with C being at -7, -4, F being at -7, -21, and E being 17 over 8. So I'm giving you lots of information here. And again, I need you to remember that in order to write the equation of an ellipse or a hyperbola, you need H and K and A and B. Well, off the bat, you're in pretty good shape. Remember, C, this stands for the center point. This doesn't stand for C as like the distance. So off the bat, you're starting with H and K, which is great. So you're halfway there. The other things that we need are A and B. Well, you need to remember from all of our qualities of a hyperbola that in order to find the focus of a hyperbola, your first coordinate, -7, just comes from H, whatever your center point was. And then the y coordinate is going to be K plus or minus C. Now, I want to deal with the eccentricity last. So you might say, well, Ms. Wonder, eccentricity, we know C over A. So C is 17 and A is 8. And though that is going to end up being true for this example, it's not always true. So that's why it's important to get as much information you can from the other stuff before you use the eccentricity, because this could be a simplified version of that ratio. Okay, now we already know -7 is H because that was given to us in the center point over here. So the next thing that we know is if -21 is equal to K plus or minus C. Now, we already know K from the center point that was given to us. So -21 must equal K is -4 plus or minus C. So then if I add 4 to both sides, then I get -17 is equal to plus or minus C. And again, that's just basically saying if I divide both sides by -1, I basically end up with C being 17. Now, since E is 17 over 8, and we have just claimed now that C is equal to 17, then that must imply that 8 is indeed going to be the value for A. So we've double checked that it's not simplified. These are the true values of C over A. Okay, so let's recap. I've got H and K, I've got A. The only other thing that I need to write the equation of my hyperbola is B. And the relationship for A, B, and C in a hyperbola is C squared is equal to A squared plus B squared. And then, so we know that C squared is 17 squared is equal to A squared, it will be 8 squared, and then we don't know what B squared is. 17 squared is 289 equals 8 squared is 64 plus B squared. Subtract 64 from both sides. B squared is equal to 225, which when you take the square root of that implies that B is going to be plus or minus 15. And there you've solved for B. So we have H, K, A, and B. The only other thing that we have to think about is which equation for the hyperbola are we going to use? Is x going to be positive in the first fraction, or should x be the one that is negative? So it's kind of good to sketch out, again, even though I don't ask for a graph, it's kind of good to sketch out the details of this hyperbola to get an idea of where are we on the coordinate plane. So if I sketch out the center point is at -7, -4. So if that's my center point, the focus is at -7, so still going 7 to the left, but way down here at -21. So if that's a focus, and that's the center, and we don't know where the vertex is, that's okay. We know that the focus, though, has to be on the inside of your curve. So in order for that to happen, and the center to still be where it is, our curve is going to be, for this one, going to be down. Of course, we know that there's also another part to the curve up top. So that means if our curve is flipped up and down, then we must need y squared to be first. Okay, y squared needs to be the positive one. So when I take these values for A, B, and C, A and B and H and K, then I plug them into the equation for the hyperbola. Now, y squared has to come first. So it's going to be y minus k, which will end up being plus 4, right? So y plus 4 squared over a squared will be 8 squared, which is 64. Hyperbola has a minus sign. X minus h will actually end up being x plus 7 over b squared, which is 15 squared, which is 225, and every hyperbola is equal to 1. Okay, so it's kind of like a puzzle, just trying to figure out what you need to fill in the gaps. Okay, last example, number 3. Also a hyperbola. So write the equation of a hyperbola with a center point of 8, -3, with a focus of 8 minus 2 square roots of 13, comma, -3, and with an eccentricity of the square root of 13 over 2. Okay, so again, they give us the center point, which is half the battle. We already have H and K. So now we just have to use our other information to go figure out what A and B should be in order for us to write the equation. So again, I want you to avoid using the eccentricity ratio for now. And if we look at the focus, we know that the focus is given by, actually, we go ahead and sketch this hyperbola again. So we got, let's see, 8, -3. So there's the center point. The focus is given by 8 minus 2 square roots of 13, -3. That's going to be one of the foci. So if you think about going to the right 8, then subtracting from that 2 square roots of 13, square root of 13 is going to be like 3 point something. So it's going to be subtracting like 6 point something from 8. So it's going to be way over here. And then going down here at -3. So this was the center. This is one of the foci. If that's the case, in order for this to all be aligned, my hyperbola curve has to go between those with the focus on the inside. So this is telling me that if my parabola is opening up to the left and to the right, I need the x squared term first. And sometimes you may want to do that first because when you look in your chart, it's going to let you know which focus equation you should look at. Now, the other thing is you can just kind of take note by the focus that they've given us here to know that, okay, this is obviously has two parts. So this is obviously given by h plus or minus c, and then we know k already matches from the center point of -3. So we know k is -3 already. So what this means is if we have h plus or minus c is 8 minus 2 square roots of 13, and we already know that h is 8, then this implies that c is going to be 2 square roots of 13. Okay, now it's important that you do the focus first because look at the eccentricity. Eccentricity is the ratio, the simplified ratio of c over a, except c is not the square root of 13. And that must clearly mean that a is not 2 because you just found by the focus, which is not simplified, that c is equal to 2 square roots of 13. So then what you have to do is if we know that eccentricity is given by c over a, then we know that the eccentricity is the square root of 13 over 2. So instead of e, I'm going to substitute in on the left side the square root of 13 over 2. Since I know c is 2 square roots of 13, I'm going to plug that in for c, and then I can use that to solve for a. So you could kind of logic your way through this. Okay, I can realize I can multiply both sides by 2, or multiply the left side by 2 over 2 to make this match. Or you can just go ahead and cross multiply. However you do it, you'll get 2 times 2 square roots of 13 equals a square roots of 13. So then if I get 4 square roots of 13 equals a square roots of 13, if I divide both sides by the square root of 13, I end up with a must equal 4. Right? And that makes sense because if eccentricity is c over a, and we found earlier that c was 2 square roots of 13, and we're now finding that a is 4, when you reduce 2 over 4, you get 1/2, which is why they give us the simplified answer for eccentricity of 1/2 times the square root of 13, or the square root of 13 over 2. Okay, so this one takes a little bit more, a few more steps in order to figure out one of your variables. So once we find a, then we know that we can use the relationship between c squared equaling a squared plus b squared in order to figure out what b should be to write the equation. So we know c is 2 square roots of 13 squared equals 4 squared plus b squared. So 2 square roots of 13 squared. This 2, by our power rules, applies to both terms on the inside. So it applies to 2 squared, well, let's just write that that's 4, times the square root of 13 squared is just 13. And that's equal to 4 squared is 16 plus b squared. 4 times 13 is 52 equals 16 plus b squared. If I subtract 16 from both sides, I get 36, which is a lovely number, equals b squared, meaning that b is going to be plus or minus 6. And there's the last piece to the puzzle. I found a earlier, I just found b, and I already had h and k from the get-go. H and k is 8, -3. We also know by the orientation of our hyperbola that the x squared term will need to come first. Okay, so our final answer will be x minus h, so it'll be x minus 8 squared over a squared, 4 squared will be 16, minus y minus k, which will change to y plus 3 squared over b squared, 6 squared is 36, is equal to 1. So that's the story with eccentricity. The last thing to talk about is degenerate cases of conic sections. And there aren't really any examples per se, like there's nothing to solve. It's just kind of like by definition of what happens in these certain cases. Now, you remember, or hopefully you remember, way back when we first learned about conics, I showed you a picture of a double right cone, and I said that conic sections were created by intersecting that cone, or that double cone with a plane, and the intersection is what created our 4 conics. Well, we have something called degenerate cases, which occur when the plane that intersects a double right cone, oh, can't spell intersects, they occur when the plane that intersects a double right cone passes through its vertex. So the 4 conic sections that are good, circle, ellipse, parabola, hyperbola, occur, anytime you slice that cone and it creates those things. But we didn't talk about, there are 3 cases about, okay, what happens when we slice the cone and it does not actually intersect, and you get those curves. When that happens, we have 3 options. We can get a degenerate ellipse, which is actually just going to be a point. And it is formed when your double right cone, actually let's do this first. Best way to draw a double right cone is to draw your 2 lines like this first, that crisscross. And then draw a semicircle to connect those on top. And then you can draw a semicircle with on the bottom, or you could use the dotted lines. It really doesn't matter. So what happens is, if we were to take the plane and intersect the cone literally exactly where the 2 cones meet on the vertex, then we get a degenerate ellipse, which is just a point. Second option, we can get a degenerate parabola, which is actually just going to be a line. So if we have our double right cone, oh, I'm not great at drawing these equal. Oh, that might have been even worse. That's okay. Alright, so when you have your double right cone, that parabola, instead of slicing at a lovely angle, what if it slices and catches the cone literally directly on this edge right here, to where we only get a line when we intersect both cones? And then the last option is going to be a degenerate hyperbola, which is intersecting lines. So we're going to get these intersecting lines if you take your double cone like this, and if the plane that you intersect it with is like directly, I'll say perpendicular to the cone, and you slice it. So I'm going to draw kind of like this rectangle. This is not the intersecting lines, but if you were to take this and cut your double right cone, as you see here, it would end up creating, we would just get both of these lines. So there's that. Those are the 3 degenerate cases of what happens when you slice your conic section and it does not create one of the 4 lovely conics that we've come to know and love.